Okay, so to start off, to finish up section 2, let's kind of start off with a demo. So I need someone up here.
That's good.
Well, it can't be me.
No, he's cameraman, so
I say the guy that said nose goes.
yeah, Keaton, you're up here.
Alright.
Don't fall. Okay, so all you have to do, just hold this kind of in the center and wiggle it back and forth. And yeah, just wiggle it, don't. Kind of tough, isn't it?
Yeah.
Alright, compared to, alright now. Now wiggle it. What's easier? With the weights at the very end or closer?
Closer in the middle.
Alright. So, what we're going to get into with this stuff, with this, all this wiggling and everything, and why is it so much harder to wiggle with the weights at the very end than closer towards the center, is because of moment of inertia. Okay, so what is moment of inertia? We've heard of inertia before?
Yeah.
What does it mean? Anybody know?
We went over it in class. I know that.
It's like the, I know this. Tendency of an object to resist change.
Yeah. Now, since we are in chapter 8, and it's dealing with rotational information, so moment of inertia is resistance of rotation. And the way that we represent moment of inertia is we use a capital I. How can we find and calculate out moment of inertia? Well, I would be equal to the mass times radius or the length squared. Now, we're going to have to manipulate this formula just a little bit, just depending upon what kind of object we're looking at. Okay? Alright, so if we're looking at a thin hoop, everybody know what a thin hoop is? A hula hoop, yes, that would actually be a good thin hoop. Here's a hoop. Okay? So, hoops, we're going to have a radius, right? So, we're working with a thin hoop and we're trying to find the inertia. Our formula stays true to what we just wrote down. Now, if we have a solid uniform cylinder that we're working with, what would be an example of a solid uniform cylinder?
Pringles.
The can.
The can, yes. Pringles can. Tires. Anything like that. Those would be a solid uniform cylinder. We're going to use... we got to put a half in front of our formula. Now this one, of course, you see that we have R. Since we are working with a cylinder, we would have a radius. Now I can't spell today. A uniform sphere. So uniform sphere will have a radius with that as well. The fraction that we're going to put out in front of mr squared would be 2/5. Okay, now, next one is going to be a long, uniform rod of length. Now this one, instead of having R, we're going to be using L. Now with this one, the axis of rotation, most of the, with the hoop, the cylinder, and the sphere, it's going to go right through the center. Okay? Right through the axis of the center. This one, we're also going to be looking through the center of the rod as well. Okay, so for this one, L is going to be a substitute for R, and the fraction that we're going to have in front is 1/12. Okay, then once again, we have a long, uniform rod of length. So once again, we are going to have L. So this time around, our axis point is going to be at the end of the rod. Okay? So at the end of the rod, find our moment of inertia. One-third times m times L squared. Then our last one. So we have a rectangular plate. And we're going to have, since we have a plate, we're going to have length and width. So L for length and W for width. Formula for this one. One twelfth, excuse me, times M. Now, this time around, we're going to have L squared plus W squared. And this would be right through the center of the plate for the axis point. Okay? So let's kind of look at an example of finding inertia for an object. Okay, so the object that we're going to look at is a twirling baton. Does everybody know what a twirling baton is?
No, can you elaborate?
Can I elaborate? Let's see if I can. Okay, so twirling baton is a rod of length with two bulbs at the end. Okay?
Okay.
Now, I do have a story for you after we get done doing all this and everything. And it deals with someone from college that I knew. What? With me. No, no, not that. Okay, so a twirling baton is a thin rod with two round objects at each end.
I thought you said two round bulbs.
This, it says objects, bulbs, objects. It honestly, it can kind of pinpoint what kind of twirling baton you want to get, because the shapes of the objects at the end do change. Yep.
Why are you saying stuff in the radio?
Get your mind out of good.
Okay, so the length of the baton is 0.65 meters. And the mass of each object at the end is 0.3 kilos. This is a long problem.
Probably simple to answer, right?
Honestly, yeah, it is. It is. All right, so what we're gonna do is we're gonna find the moment of inertia if the baton rotates about the midpoint and at the end of the baton. And I think this marker is about done because this is getting kind of light.
Yeah.
We're going with Christmas colors today.
Yeah.
All right, so
I celebrate Hanukkah.
you might gonna need to borrow a calculator. Okay, I'll get calculators out. If you need to borrow one, come get one.
Oh, this one's
I'm gonna put you on camera. With
Oh,
stuff.
some right there. Just leave it right there. Okay, so for the first part, finding what the moment of inertia is when the baton is rotating about the midpoint. The easiest way to do this is to kind of work with 1/2 of the baton. Okay? So since it's rotating about the midpoint, we need to figure out what is that length. So to find our R, we're going to take 1/2 of the length of the baton. So 1/2 times 0.65 meters. All right, so 0.65 divided by 2 is
0.325.
0.325 meters. Okay? So what we're going to do is, since we're working just with one end, we're going to find the inertia with one mass, since it has the two bulbs at each end. Okay, so find inertia at each end. Take the mass of the bulb, 0.3 kilos times our radius squared. 0.325 meters squared. Okay, so let's kind of run that through a calculation. Let's see what we come up with. 0.30 times 0.325 squared. I'm coming up with 0.032 kilograms meters squared. Anybody else kind of coming up roughly to that same number? All right, so now that's just the mass with, that's just the inertia at one end. We got two ends of the baton, right? So to find the inertia of the baton, what we're going to have to do is take 2 times the inertia of the one mass. So 2 times 0.032 0.064 kilograms meters squared.
Where's the 1/12 go?
We're not using the 1/12 in this situation because that would just be if it was just the rod itself without the mass on either end.
Okay.
Since it has that bulb on the end, we can't use the formula for just the rod.
Alright.
Okay?
So then you just get rid of the 1/12 then?
Yeah, we don't worry about that that part of it.
Alright.
I was wondering if anybody was going to ask that question or not. Okay, so now inertia if it's twirling about the midpoint. Now, finding the moment of inertia if it's twirling at one of the endpoints. Well, make sure I'm thinking correctly. Yep. So we're just going to use I is equal to mr squared. What's our mass?
0.3.
What's our R?
0.325.
Not this time around.
Oh, it's gonna be the whole thing.
It's going to be the whole distance of the baton. So instead of taking the 0.325, we're going to be taking the 0.65 meters. Point 0.3 times 0.65 squared. Now coming up with right around 0.13 kilograms meters squared. All right, so looking at your numbers, which one would have the more or the greater moment of inertia? Twirling upon the midpoint or twirling at the end point? The end point, okay. So why is that?
Because when you have the thing on the end and like the forces going around,
Yeah.
it propels it with it.
Mhm.
More leverage.
More leverage. Okay, so here, if we just look at the yardstick, if we hold it right in the middle, pretty easy to do. Hold it at one of the other ends and and if we put some weight on it at the end, yeah.
Do what you want. Send it into the wind.
No, I know I won't. Okay. Now, we're going to kind of go back and talk about one of Newton's laws. We're going to talk about Newton's second law for rotational motion. Now, Newton's second law does anybody remember Newton's second law?
No.
feel like I should. Oh,
Acceleration
is equal to an object.
is equal to
1
F over M.
force
F over M. Yeah.
over mass.
That was a tough.
Close
Okay,
with the 1.
so how does this relate to Newton's second law of rotation?
You got me.
Well, we learned this the other day, that we have angular acceleration is directly proportional to net torque and inversely proportional to inertia. So what in the world is that formula going to look like? Okay, so what is the symbol that we use for angular acceleration? Not the W,
Not the W.
that's angular velocity. What? Alpha, right. So, alpha is equal to, and if we look at the definition that we just wrote down, it is directly proportional to the net torque. Well, if it's directly proportional to it, is if one goes up, the other one goes up, right? So that they are equal to one another. All right, so net torque, I can't do the Greek T, so that's why it just looks like a regular T. And is inversely proportional to the inertia. Now, if something is inversely proportional, one goes up, the other one goes down. Now, if we look at that formula-wise,
1 over
1 over the I. So, net torque over inertia. Okay? Questions? Any kind of questions so far? Alright, now let's kind of look at an example of Newton's second law of rotation. Okay, a solid steel wheel. So what kind of shape would a solid steel wheel have?
Circular.
Well,
Yes. Can we be a little bit more elaborate?
Round.
cylinder.
What kind of cylinder? A
Uniform.
uniform,
Solid.
solid cylinder. Okay? So keep that in the back of your minds. Okay, this wheel has a mass of 15 kilos and a diameter of 0.44 meters. It starts at rest. You want to make it rotate at 8 revolutions per second in 15 seconds. Now for this problem we have 2 parts to it. We're going to break it up. We'll do A, talk about that, then we'll do B. Alright, so A what torque must be applied to the wheel. Okay, so to figure out what the torque is, we're going to be using our formula that we just wrote down for angular acceleration. So we're going to be using this formula. So to get torque by itself, how do we do that?
A times,
Yeah,
Alpha times I.
net torque is equal to alpha times I. So now what we just need to do is figure out what is our angular acceleration and our moment of inertia. Which one do you want to work with first?
inertia.
Inertia, okay. So inertia is equal to, now we said that our wheel is a uniform solid cylinder, right?
Yep.
So what is the formula for inertia for a uniform solid cylinder?
1/2 mr squared.
Okay, half mr squared. So our m,
Is 0.22.
no, m is mass,
Oh, yeah, I'm
15 kilos times, now what's our r? Well, they said that the diameter of the wheel was 0.44 meters. R stands for radius, right? So what's the radius?
diameter.
0.22. We gotta square that. 0.5 times 15 times 0.22 squared. And what are we coming up with?
0.363
0.363 kilograms
times meter squared.
meter squared. Is that what everybody else is kind of coming up with? Okay, any questions there? Nope. All right, so now we got to look at angular acceleration. Well, for angular acceleration, at the beginning of the chapter, it said the way that we can figure that out is we take the change in angular velocity over the change in time. Right? Okay, so let's look at this formula. Change in angular velocity. Well, we know that we want it to go 8 revolutions per second, right? But if we're working with angular velocity, we don't want it as revolutions per second, we want it as radians. Okay? So what do we apply with radians?
16 pi.
No, not 16 pi.
8 pi.
2 pi.
Oh, I thought.
Okay, so since it's in, we want, with angular velocity, angular acceleration, we want the units to be radians per second squared. So to get it for radians, we're going to take 2 pi times our 8 revolutions per second minus, it's starting from rest, so guess what that would be? 0. And since it's 0, I mean, can we put revolutions per second? Yeah. Over, what's our change in time in this situation? 15 seconds, because that's the time that was given to us.
See, I was right, 16 pi.
True, but go ahead and take it times 3.14. Okay, so go ahead and run this through your calculator and let's see what we come up with for our angular acceleration. Okay. 3.35, and what should the units be for this? Radians per second squared. Okay? So we have our angular acceleration, we have our inertia. So to find the torque on the wheel, all we have to do is just multiply those two numbers together. Alright, so that torque is equal to 3.35 radians per second squared times our inertia, 0.36 kilograms meters squared. So 3.35 times 0.36, what's that come up with?
1.22.
1.22. Now, we're finding torque, so what's the units for torque?
Newtons times meters.
Newtons times meters. Okay, and looking at our units, you know, that radians unit gets basically kind of dissolved away. What are we left with? Kilograms times meter squared per second squared. Well, excuse me. Kilograms times meters per second squared. Mass times acceleration gives us force, which that unit is newtons. Then we're left with 1 of the meters. So that's how we get the units for the torque. Okay? Any questions there? No? Well, let's fix something on this camera because I kind of see it's happening again. One of the legs was a little short. Okay, so any questions with part A?
Just twist the camera around and use that as the back leg.
I got it. I think it's
One of the
good.
other legs short?
I think it's good now.
What?
I think it's good now.
Nope.
No?
There we go.
Oh, now it's pointing down.
All right, so question B. If you apply the torque by wrapping a strap around the outside of the wheel, how much force should you exert on the strap? Okay, how do you think this one's gonna work? Hold on, I'm gonna hit